Okay, so this is Dr. Liu. I'm going to discuss how to analyze data for the standing wave lab. Uh, so let's get started with looking at the data set. Here's our standing wave, the mass we need in order to sustain or stabilize those how many half waves. So each peak and valley is a half wave, not exactly a full wave. A full wave will be actually two of them, but if you're vibrating back and forth, that means you have to have two of these peaks and valleys to make a full wave. So these are the masses. I did this with this particular set. So well, these students could actually check their numbers against mine. I got mine carefully. I spent a whole half hour. For me to have spent half hour, it's quite a bit of time. So these are all the masses I have up to the 1.8-ish kilograms of weight. And this number that is in green is not really measured but calculated. What would happen if I really wanted the very one half wave or the jump rope shape? I would have to load this thing with 8 kilograms of weight. And guess what happened with even 1 kilogram? One of the strings actually snapped. So this is something that we shouldn't be pursuing. We should just be theoretically calculating for just for fun. We don't need this. So this first column is just everything in grams. And someone asked about tension. What exactly is tension? That would be the weight. So the mass times gravity, but the correct mass unit should be kilogram. So the tension calculation should be this column divided by 1,000, then times 9.8, right? 9.8. So here, if I just go ahead and show the formula, A3 over 1,000 times 9.81. I did 9.81. All right, so that's tension. Okay, and the number of loops, these I just typed them up, 8 loops, 7 loops. But in case you want to automate these numbers, say if I didn't really have these numbers here, and I only entered two of these numbers, I can select them and go to the bottom right corner and start dragging. These automatically generate these numbers out, right? Because you have 8, 7, and that sets the trend as decrementing one at a time, right? So now they're back. Right, so that's a little trick in case you didn't take the first semester of physics with one of us and you didn't get to see this trick. Okay, so calculating the wavelengths, and as I said before, the wavelength is well the whole length of the string. That's right here, C12. This is what I did. I measured it. I only did it myself. Two people would have done it more accurately because one can just hold one end, the other person looks at the other end. I cannot really look at one end while holding the other end. I have to be much taller if I wanted to do that all on my own. So this is a little estimate, 1.48 meters. And the frequency is 120 hertz. We have it from the 60 hertz of AC and vibrate 2 times to create 120 hertz. All right. So to find the wavelengths, this is how we're going to do it. This formula, you multiply the length of the string, the L, by 2L, and then you divide by how many of these loops you see. So the first one is 8 loops. That means we actually have 4 full wavelengths on the string. Every two of the loops is one wavelength. All right. So now that means if we have 2 loops, that is exactly one wavelength for this whole string, right? So let's see that right here. 2 loops, this is one wavelength. And the formula is just the same as I pointed out. I refer to this cell, and the dollar signs here means I'm fixing the reference. So if I automate my formula down the entire column all the way down to say column 10, then the C12 stays as C12 because I only need to refer to this one cell, right? And the C3 will go to C4 to grab the 7 for the next cell, right? All the way down to C10 to grab the 1 from this cell to calculate the wavelengths. So that's from automation, dollar sign C, dollar sign 12, that fixes the reference. So if I just click outside, if I click in one of these other formulas, still C12 with dollar signs, but this other number is C6. Basically, relatively speaking, to the left of the cell you're calculating, but the C12 with the dollar signs are absolute references. Okay, so that's how you would calculate the wavelengths. Just take twice the length of the string, divide by how many loops you observe. Right. Okay. So what about the square of the wavelength? Well, you just square the this cell. Well, you don't need to fix D3 because the next cell below it will require D4. The next cell below it will require D5. Right? We're just squaring it because the relationship is linear only if you square the wavelengths. We'll get to it in lecture soon enough, but this is the relationship between tension and the wavelengths is the square of the wavelengths is proportional to tension. All right, so I can rewrite this a little to make it more um, understandable. What we're doing here is 1 over mu f squared. Oh, I see. I got it outside of the formula. Okay, here inside the formula. Right, that's good. Times t. Okay, so let's resize that a little and move it to some other place. Okay, that's better. Okay, so what I'm looking at is the square of the wavelength is proportional to tension, and the proportionality factor is this factor here, which includes the frequency squared and also the density of the string. Density of the string is how much mass per length. So you could say a kilogram per length, or per meter. That would be if you have a meter, the string will weigh 1 kilogram. That's like a thin bar, right? The string is much less dense than that, and we have an expected value. I'm supposed to tell you. So let me divulge the number 0.000. So 3 zeros, 634. So someone measured it some time ago. And I cannot track down how it was measured, how accurately it was measured, who did it, but I was given this number about 2 decades ago, and I was not able to confirm this value, but I got close. So let's look at the calculated value based on my measurements. It's 0.30561. So 56 to 63, there is what 7 out of 50-ish, 60-ish. So a little over 10% of uncertainty, a little less than what I really wanted it, but that's what my values are giving me. So let's see how I calculate this mu here. So back to the calculation here, we have the square. So if we look at this formula, I should be able to plot T tension as x and the lambda squared as y. And that's what these dots are. They're not evenly distributed because they're, yeah, if you look at the squares, right, start from 1, 3, then 1, 7, 2, 4, and 1 all the way up to the 2.1. The spacing in between, like in between these two, is 1 meter squared. And spacing in between these two is what, 0.4 meters squared. That is because we're squaring these values. Even I plot these out, they won't be evenly spaced out. So this is what I really wish I could do, is I could get in between these values, right? There's a big gap, but I cannot because the wavelengths are fixed to the length of the string. I can only fit how many integer number of half wavelengths on the string. So that's what I can do. If I do a two loop, right? That is the next thing I can do from a three loop. So from a three loop, I get 0.9, which is this value if I read vertically, and then from two loops that I got 2.19. This value is vertical coordinate. So in between, there's nothing I can absolutely do because how I'm fitting these exact loops on the same length string, right? So that's basically there's nothing I can do with it unless I have different length strings that I calculated out these values. They will fall in between or maybe around this dot a little bit, just like I have 10 groups, 9 groups, right? Including myself, still actually 9 groups, because we have used 9 sets of apparatus. We'll have some values around this dot, but not really filling in between unless I have really different lengths across the lab groups. I don't intend that to happen. I want that to be close to about 1.5 meters so that everyone's values like weights will be close to what I start, right? So don't be worried about all these gaps. These are gaps that are basically from based on the length of the string being very similar. With one student group, you absolutely cannot fill the gap. And even with multiple groups, you can only expand each data point to a small extent. All right. So now we have these, we're supposed to be plotting. So if you just highlight these, right, I hold down the control. I don't remember what I use for Macs because I don't have my Mac anymore. And then do this control on the PC. You can select these 2 columns, insert a graph. So I'll just show it over here. Insert charts under this scatter. I'll do a scatter chart. See that? That's exactly what the other one was, except that that other one had more details, right? So once I insert that, I need to make sure it has all the details, such as the axes, the labels, the chart title, right? So the labels have to be representing what exactly you're plotting. I think I'll change it. See that? It's a very long line here. It doesn't correspond to the right thing. So I single click and press equal, and I click this right here. Well, it's still exactly the same thing, except that this is referring to this sheet. I had another sheet I copy pasted data from a decade ago. That was the label was still referring to that sheet, so I'm changing it. Same thing here. So click this, which is probably an empty entry if you just started the plot, and hit equal and scroll to the horizontal label, hit it and hit enter. So that will give you all these. And that one over there is the label of the entire graph. I typed it up right here just so that I can refer to it. Single click, hit equal sign, hit this, and then hit enter. Well, nothing changes, yeah, but I can say this, standing waves on a, see that it updates that label. So I like all the links together because if you want to write something, you may as well just keep those links. You only have one copy of each. Say the tension. If I wanted, I can change that tension to T because I had this symbol T, right? So if I hit enter, see that turns into T. So everything is consistent. Instead of, oh, I have tension or I have T somewhere else, referring to the same thing, I would have them linked together just for clarity. So once I plot this out, I can right click on one of the data points. I think these are all just kind of reviews in case you have forgotten, and just go and insert a trend line because I already have a trend line. I'm told to format the trend line. So otherwise, you would actually insert a trend line. And once you have that trend line, and make sure it's linear, and also you have these 2 boxes checked. The equations displayed, R-square values displayed. So let's get rid of those. Those are already done. And someone was saying, oh, R-square value is equal to 1. That's almost like fake data, right? Fake data has R-square value equal to 1. But I did show that it was 0.999 something. It wasn't exactly literally 1. So it was just not showing all those sig figs. All right. So what do we do next once we have this fit? Well, we take this slope, right? 0.1239. That is supposed to be the 1 over mu and f squared, right? And we can calculate back the mu. So let's show the mu calculation now. Okay. So 1 over b15, which is the slope, right? 1239, and then over C13 squared, which is the frequency 120 hertz. So 1 over the B15, which is the slope and over the frequency square. So that calculates back into the string's density in kilogram per meter, because everything was in seconds, was meter, and also kilograms, right? I converted all the grams into kilograms when I calculated tension, right? So now we have this value 561. And something I slashed out because this was from a calculus-based class. I didn't have to calculate this for algebra-based class. And here's an expected value. And unfortunately, it doesn't really conform, but that's also not required for this class. So let's remove that. And what is also required is calculate a relative error, which means expected minus actual experimental divided by the expected in a percent style. So let's do that calculation. And I want to slap an absolute values function, because expected and measurements, one could be bigger than the other. In this case, the measurement is less. So the difference between measured and expected and divided by expected, which is somebody giving that value. Maybe I should reevaluate what this value is and where it came from. And if I can have a big spool and I put them on an analytical balance, I just weigh that myself, I may get a slightly different answer. I always suspected that. But let's say that we trust this value. So okay, not B21. I was clicking this. Okay. All right. So difference between measured, this value that's calculated based on measurements, we'll call that measured, minus the expected, the red, and divide by expected. And I click it, go to home ribbon, and turn this into a percent style, a 12%. So that's what we're looking for. What is your relative error? You don't have to say whether you confirmed it or not. And in my calculation, it seems like I couldn't confirm it, but that's okay. I think a 10% error would be something I really like, but 12% is okay. So let me stop the video now.